Okay, let's try this. So Professor Gray has shown us the importance of the state parameter, the combination of effective stress and density of the soil, and has shown a framework that allows us to understand soil behavior under both loose and dense conditions, under high effective stresses and low effective stresses, under monotonic loading. And we'll see now that that same framework applies to the behavior of soils under cyclic loading conditions, the kind of loading conditions we anticipate during earthquake shaking. And so some of my slides will repeat some of the concepts that he's just talked about, but that's okay because they're so important that we want to make sure that we understand them. The notion of a soil being initially deposited in a loose state or a dense state can be illustrated in a number of different ways. We understand that the soil will, the soil, if it's in an initially loose state, will have relatively high void space or high void ratios. And in order for it to be sheared under drain, if it is sheared under drain conditions, these particles will slip and slide relative to each other. The void space will be decreased. The height or volume of the soil will decrease as it contracts. But if we start in an initially dense configuration, then in order for shearing strains to develop under some applied shear stress, the particles are going to have to slide and roll up and over the underlying particles, and the void ratio will increase and the soil will expand in its volume or dilate. We have a steady state line that illustrates the relationship between the void ratio or density of the soil and the effective stress when the soil has reached the steady state, when it's shearing at large strains. If we have an initial state that plots above that steady state line, the soil is going to exhibit contractive behavior. If it plots below, it's going to exhibit dilated behavior, whether we have undrained or drained loading conditions. During earthquakes, we're primarily concerned with undrained loading conditions when these soils are saturated. And so if we have soils that are initially below the steady state line, they will tend to dilate, and under the requirement of constant volume undrained conditions, the void ratio can't change. So the way they get to the steady state line is to generate negative pore water pressures. The soil particles are trying to expand. The soil is trying to expand. The voids are trying to increase in volume, but the water is there. If the soil is saturated, that water pressure is going to go down. And the extent to which it goes down depends on how far away from the steady state line we are. If the soil is in an initial state that plots above the steady state line, it's going to be contractive, and its tendency to want to contract for the voids volume to decrease is going to be resisted by the water, which can't escape the voids of the soil under undrained conditions. Consequently, the pore water pressure will go up, the effective stress will go down, and will exhibit contractive behavior. The effective stress will go down until it reaches the effective stress that corresponds to the steady state line for its density. So here we have soils, 5 elements of soil that all have the same void ratio but at different confining pressures. They all have the same relative density since they have the same void ratio, but their behaviors are very different. So so it's important for us to remember, as we've just heard, it's not just the density of the soil that matters, it's a combination of the density and the effective stress. That defines the state of the soil, and it tells us how the soil is likely to behave. So we will end up at this steady state point. In reality, there's another dimension. There's the shear stress, which is illustrated by Q here, the deviator stress. And our steady state line actually is a curving line in 3 dimensions. We tend to look as though we're up above this diagram, and we look down to axes of void ratio and effective stress, so we're looking down upon this. But this line follows our failure envelope, and it will intersect the failure surface at different points depending on the density of the soil. So for the high void ratio, we'll intersect the failure envelope at a low effective stress level. But as our density increases and the void ratio goes down, this line will curve, and at a higher shear stress level and a higher mean effective stress, it will intersect the failure surface at a higher point. And so it's useful to think of where this line is curving for a looser sample and a denser sample. And studying a figure like this will help you understand how things are behaving at different effective stress levels. And so, as we've seen, under monotonic loading conditions, we can, in very loose soils, we will be at say, a point that looks like this, where we're intersecting the failure surface at a very low effective stress level, consequently a low shear stress. So our point is going to be, our steady state point will hit the failure surface at this location. The soil is very loose, it's going to be very contractive. After perhaps initial, initially it will contract, and then it will contract very quickly and flow down to this steady state point. We'll see initially high shear stress, it reaches a peak at a low strain level, and then we'll see dilated behavior as we strain towards that critical state or steady state. A very dense sample is going to be, after perhaps an initial contraction, it will tend to dilate and go up to a higher point on the failure surface because the steady state pressure, effective stress for a denser sample, lower void ratio, is going to be higher. And we'll see a more ductile response in terms of the stress-strain behavior. And soil at an intermediate density will have a steady state point that's at an intermediate level. It will build up pore pressure, and then at some point will reach the phase transformation line, and the soil will change from a contracted state to a dilated state. It will dilate up the failure surface until it reaches the corresponding steady state point for its density level. So we see this kind of behavior occurring under monotonic loading conditions. If we load the soil under cyclic conditions, let's imagine that we have a dry sand and we start a loading process. So we're going to apply a harmonic load to it, a sinusoidal load, and so we'll go from our initial point up to a peak shear stress at point A. This is really the first quarter cycle of the cyclic test, and it's equivalent to the beginning of a static test. We go up to point A, the soil provides some shearing resistance, some strain develops. Because it's a drained test on a dry sample, there's no change in effective stress. We simply increase the shear stress, and there's no change in effective stress. If we cycle the sample and subject it to multiple cycles of loading, it exhibits nonlinear inelastic behavior. It goes down to point B. The shear stress goes down to point B. There's still no change in pore pressure because the pore fluid is air, and air is very compressible, so it provides no resistance to the contraction of the sample that would occur if it is a denser soil. Then we go back up to point C. We've completed a hysteresis loop. We've gone up, then down, and then back up again, and we see nonlinear inelastic behavior here. Under drain loading conditions, if we have multiple cycles, our stress path is simply going to go up and down, up and down. We're looking now at shear stress versus vertical effective stress. our sample will exhibit nonlinear inelastic behavior. It may soften, it may stiffen if it's a soil that's densified under this loading condition. If we have undrained conditions, though, we'll build up pore water pressure. So as we go from our initial point up to point A, the contractive tendency of the soil will cause pore pressures to increase. Remember that a dense soil will initially contract at small strain levels before it dilates. And so even a dense soil will build up some pore water pressure in its early stages of loading when the strains are relatively small. Then we'll reduce the loading and go down to point B, and as we do that, we'll build up some more pore water pressure. So the effective stress at point B is going to be lower than the effective stress at point A. And as we go up to point C, we build up some more pore pressure. Down to point D, we build up some more pore pressure. So the effective stresses are reducing during this cyclic loading. As the effective stresses get smaller, the stiffness of the soil decreases, and so we see our hysteresis loops starting to bend over a little bit more, and the soil becomes softer. That's exaggerated in the diagram like this, but this is the process that occurs. Eventually we'll get to point G, and when we go down to point H, we see a little bit different behavior in here that's due to phase transformation. The soil at some point will hit the phase transformation line, and it will start to dilate. And when it dilates, the pore pressure goes down and the effective stress goes up a little bit. So when we have a reversal of stress, say in our first quarter cycle, we come up to this point, and then we have a reversal. Depending on how contracted the soil is, that will control the path it takes upon this reversal. If it's not very contracted, it will come down almost vertically, and we won't see much change in pore pressure. We won't see much of an increase in pore pressure. But if it's more contracted, it will follow a flatter path down, and the rate of change of effective stress to shear stress is going to be greater. So different soils with different densities, different effective stresses, different state parameters will behave differently upon cyclic loading. And you control that state parameter, control how contracted the soil is. If we look at an element of soil now subjected to drain loading conditions, where the concept of shear stress amplitude being applied, if we look at the first cycle of loading now under drain conditions, you see that the soil contracts, it densifies. So we're seeing a positive volumetric strain. Here, the soil at the end of this first cycle is denser than it was. It will also be stiffer than it was. If we follow that first cycle in our stress strain diagram, it's softer because it has a lower density. But it has densified, it's strained during that first cycle. So the second cycle will experience a smaller change in density, and the soil will be stiffer in the second cycle. So the second cycle will come around, come down here, stiffer, and back up again. And because it's stiffer, it will strain less. The shear strain will be lower in the second cycle than it was in the first cycle. And with subsequent cycles, the soil will become denser, so it becomes stiffer, and the shear strain amplitude will decrease as the soil strains more and densifies more. So this is all consistent with this steady-state framework, the state parameter framework that Professor Gray described for static loading conditions. These are implications of that for cyclic loading conditions. Now, if we look at an undrained test on a sample of sand, we can plot a response in several different ways. And we're going to look at this figure in some detail. We have stress strain curves on the upper left. We have a stress path, shear stress versus vertical effective stress on the upper right. Down below, we're going to have this normalized effective stress plotted as a function of the number of cycles. And here we're going to have the shear strain plotted as a function of the number of cycles. So in our first cycle, we come up, we have some reduction in effective stress. pore pressure is generated, we come down, we go back to here, and we've completed our first cycle of loading. The effective stress is only reduced a little bit, maybe 10% of the initial effective stress, so we'd say we have a pore pressure ratio of 10% there. The stiffness of the soil, the self-stain diagram, is quite high, so that small change in effective stress hasn't led to much softening of the soil, and we can see that the shear strain down here is quite small. Over here, we see that our effective stress has only been reduced by perhaps 10%, something like that, or maybe even less than that. We have a second cycle of loading, and we get some more buildup of pore water pressure. The effective stress has reduced a little bit more. It's still pretty stiff. After 5 cycles, let's say, now our pore pressure, our effective stress is about 75% of the initial effective stress, but the stiffness hasn't reduced very much. Our strains are still low after these 5 cycles. After 10 cycles, we're at about a 40% pore pressure ratio. So our effective stress is about 60% of what it was, maybe a little higher than that, maybe 70%. Our strains are still small. After 15 cycles, the strains are still small. And at 15 cycles, we have lost almost half of our effective stress. But the stiffness of the soil doesn't vary linearly with the effective stress. The stiffness stays relatively high until the effective stress becomes very low. So we have continuing numbers of cycles. By the time we get to 20 cycles, now we start to see some softening of the profile. After 20 cycles, our pore pressure ratio is about 2/3. We have only 1/3 of our original effective stress remaining, and now we start to see our soils becoming softer. Our strains have become larger now. We're at a pore pressure ratio of about 0.6 or so at this point. So we have 40% of our effective stress remaining. But now we come down in our 21st cycle, 20th and 21st cycle, we start to hit this phase transformation line, where we change from being in a contractive state to a dilated state. Our stress ratio here, the ratio of shear stress to vertical effective stress, is fairly high. These soil particles now, even in this undrained test, have strained and arranged themselves in a configuration where they're able to resist a shear stress in that direction, that positive shear stress. Then when we have a reversal, we get more contractive behavior. So when we cross that phase transformation line, the soil particles arrange themselves in a very efficient way. It's as though somebody's pulling on a rope, and I'm trying to resist it, and I'm going to have my legs in a position where I can resist that. If all of a sudden somebody pulls the other direction, I can fall, because I'm oriented in one preferential direction. So as our number of cycles begins to increase beyond 20, the soil becomes more contracted, and it will come down, hit the phase transformation line in the other direction, and then dilate. And it dilates until there's a reversal. Then it becomes very contractive. Our effective stress goes down to quite a small low value here in this cycle. Then we hit the phase transformation line and we dilate back up to this point. Now we're in the 25th cycle, another reversal. And we're going to some very low effective stresses here. And then we dilate to much higher effective stresses. As we dilate, the pore pressure is going down, the effective stress is going up, and the stiffness of the soil is going up. And as the stiffness goes up, we see that the soil will become stiffer, and we get this kind of shape of our hysteresis loops that has some very flat portions here where the effective stress is low, but then the soil will dilate and it will stiffen. And so we get hysteresis loops that are kind of in the shape of a banana. They're unusual. They're unlike the shapes that we have conventionally. We can see that once we get to this stage where we're getting phase transformation behavior, our strain amplitudes start to increase very quickly. So our strains are small until we get to pore pressure ratios of maybe 80 to 90% or so. And then the soil becomes much softer and the strains become much larger. And we see this manifested as liquefaction, cyclic mobility. We define initial liquefaction in terms of pore pressures or effective stresses. And we say that initial liquefaction occurs when our pore pressure ratio reaches 100%, which means that at least momentarily, for a small period of time, we have zero effective stress. That doesn't mean that the soil has no strength, because as we apply shear stresses, that soil is going to dilate, and the stress path will move up along this deluge surface until we have a reversal, or it will continue until we reach the steady state point. But as it dilates, the effective stress is going to go up, and the stiffness of the soil will go up, and we'll have some strength that we can resist. Ultimately, it will be that steady state. When we have non-plastic soils, we tend to see an exaggerated sense of this kind of behavior. Here's some laboratory tests on a silt that's non-plastic. It exhibits relatively stiff behavior in the early stages of loading. And then once liquefaction has been triggered and we reach high pore pressure ratios, the soil becomes much softer. It will dilate and increase its stiffness. Then it comes down, and we have a very low stiffness here, but it will start to dilate and stiffen up, follow this path. We have a reversal, it comes back down, becomes very soft, and then it dilates and follows a path that looks like this. When we test plastic silts, here at PI of 10.5, under the same kind of loading conditions, we see that the softening of the soil is much more gradual. We see that the tendency for it to stiffen as it dilates is reduced, and we see a much more gradual buildup of strain. The areas of these hysteresis loops are different. This is in a more plastic material. We're seeing a broader hysteresis loop. It's not as pinched as the hysteresis loop in cleaner soil. And so for a non-plastic soil versus a plastic soil, we see some differences. And we'll find that pore pressures don't build up to such high levels in the more plastic materials as they do in the non-plastic materials, at least at relatively modest densities. When we have very high densities, as Professor Gray will talk about a little bit later, plastics, non-plastic soils, the very dense ones, can exhibit behavior that looks more closely approximated as the plastic soils. So, in comparison of tests on 3 silts under similar conditions, we see a non-plastic silt given by the black line. It has a very pinched hysteresis loop at a particular strain level. The higher plasticity material at the same stress level has broader hysteresis loops, and one with intermediate plasticity has an intermediate shape to its hysteresis loop. So if we look at the early stages of the test, if we go from point A to B to C to D, we build up a little bit of pore water pressure. We have a modest degree of nonlinearity. The hysteresis loop is relatively thin, indicating not a lot of energy being dissipated, not a lot of nonlinearity. But if we apply multiple cycles, eventually we'll work our way over to where our stress path is looking something like this. At point E, we've crossed the phase transformation line. We dilate up to point F. We have a reversal that brings us down to point G, where we hit the phase transformation line on the other side. We dilate to point H, and then we come back down upon another reversal and reach something like point E again. Because this effective stress during this cycle is changing, it's both increasing, increasing and decreasing. We see changes in stiffness, that cause our stress strain curve to become very flat. Say at point E, and point G, where the effective stresses are low. And as the soil dilates and the effective stress goes up, it stiffens to point F in this direction and to point H in this direction. If we look at this behavior in terms of stress strain and stress path curves, we have a failure surface and we have a phase transformation line that is at some fraction, usually 2/3 or 3/4 of the slope of the failure surface. If the soil is below the phase transformation line or between the two phase transformation lines, we will see contractive behavior. But once we go beyond it, we'll see dilated behavior. And so if we have an element of soil that starts out at some point with no shear stress, and we start increasing the shear stress, it will be contractive. Pore pressures will be increasing. The effective stress will be decreasing. The soil wants to contract, but there's water in the voids, and the water can't get out under undrained conditions, so the water pressure goes up. As we approach the phase transformation line, that rate of contraction decreases, and when we hit that phase transformation line, the soil's changing from contractive to dilated behavior, and so it doesn't want to contract or dilate, which means that the effective stress is constant, at least momentarily, which means that this diagram, this curve, becomes vertical. Beyond that point, the soil dilates, and it will continue to dilate until we get a reversal of stress or until it reaches a steady state point. If we have a looser soil that's more contractive, it will generate more pore water pressure in that loading. If it's less contractive or dilated, it will generate less pore water pressure and dilate more strongly. If we apply shear stresses in the other direction, we get the same behavior in the other direction. If we have a cyclic load being applied, we'll see that the pore pressure increases, and it increases incrementally. This is my chance to get a drink of water. While you watch the magic of PowerPoint, and you appreciate how long it took me to make this thing work. I'm capable of wasting many hours on PowerPoint. So we build up pore pressures incrementally. Every cycle of loading is causing an increment of pore water pressure. And that means the effective stress is reducing. And that effective stress will continue to reduce with each cycle. But now we're starting to get close to the phase transformation line. It's a low level of loading. The shear stress is small here, so it takes a lot of cycles to build up pore water pressure. But once we hit that phase transformation line, the soil will become more contractive. And it will dilate when we cross that phase transformation line. We see an increase in the rate of pore pressure generation, but then we see this dilation occurring when we cross it. And so we'll go in more and more cycles, we'll see this kind of behavior, and eventually we may reach a condition of initial liquefaction, where our pore pressure ratio is 100%, our effective stress is at least momentarily zero, but as soon as we continue to increase the shear stress, it dilates. And so we'll have multiple cycles occurring. And what we'll find, typically in the test, is that we reach a constant stress path, effective stress path. And so we'll just go back and forth, and we have this stress path that looks like maybe a butterfly or something, back and forth with constant effective stresses. Now, if we're trying to model this behavior, our constitutive models typically relate the behavior of the soil to the effective stresses. So if the effective stress is stabilized, a typical model that's based only on effective stresses would have the strains stabilized, and we wouldn't get any additional strain occurring. But we know in the laboratory tests that we do get strains developing, even after we've reached this constant state of effective stress. And we attribute that to damage or alteration of the fabric of the soil. And that tends to cause an additional component of softening that's not explained in terms of effective stresses. And so to model this behavior, we have to model the fabric of the soil and the degradation of that fabric with increasing numbers of loading cycles. Now, if we apply a higher shear stress, under cyclic loading conditions. We may, even in our first cycle, reach the phase transformation line, and it won't take very many cycles of loading to build up very high pore water pressures. We'll see that our effective stress decreases from one cycle to the next, but we'll also see increases and decreases in the effective stress even within a single cycle of loading. And so we can expect our stiffness to be changing from cycle to cycle and within individual cycles. And so if we start out in our first cycle and apply a cycle of loading, at the end of one cycle, we've developed some pore water pressure. Our effective stress has decreased. The soil still has a high stiffness. If we go through a second cycle of loading, we'll build up more pore water pressure. Our effective stress will be lower at the end of the second cycle, but we still see typically a high level of stiffness. If we have many more cycles of loading, we'll eventually reach a condition where we start to have low effective stresses, but we hit the phase transformation line and we dilate up the failure surface until we have a reversal. And now we can see that we're starting to have some decreased stiffness. And so we have a greater strain. We contract, go down to the phase transformation line. Now we have a low effective stress, and the stiffness of the soil at that point is lower. But we reverse and dilate, and so the stiffness increases. Then we contract, reach an initial liquefaction state. The stiffness of the soil can be very low at this point. We have a high pore water pressure, a low effective stress, and a softer soil. But we're still going to dilate and regain some stiffness. And so if we look at the stiffness of the soil, as we follow a hysteresis loop, you probably don't want to even try to follow along in the pages here, because I can click faster than you can turn the pages. Just watch the screen, and then you can catch up. The stiffness is going to change throughout this cycle of loading. When the pore pressure becomes very high, the stiffness becomes very low. But then the soil starts to dilate, and as it dilates, the stiffness increases. And it'll increase until we have a reversal, at which point it's momentarily stiff, but then we come along and we reach a high pore pressure again. The soil becomes very soft, it strains easily, but then it starts to dilate, and it will dilate until we have a reversal, or until we go all the way up to our steady state point. Okay? Now you can catch up. Turn pages. This is an interesting diagram that shows some of the effects of this phase transformation behavior and the dilation-induced stiffening that occurs. This is a result of a nonlinear effective stress analysis. What we're showing here is the acceleration at different points within a soil profile. It's a 20-meter thick soil profile. The bottom 10 meters is a stiff clay that doesn't generate any pore water pressure. The upper 10 meters is a loose sand that does generate pore water pressure. And so you see in the early stages of the loading, these bands of color reflect the acceleration levels. Positive accelerations are light in color, negative accelerations are dark in color, and these bands are almost vertical. They actually have a slope to them that reflects the shear wave velocity of these waves as they travel from the bottom up to the top of the soil layer. So they'll come up, they'll go back down, they'll bounce around, and at this stage, in the early parts of this loading history, there's very little pore water pressure being generated in this upper layer. But as we have more and more cycles of loading, we start to see more pore pressure being generated. So here we have a negative acceleration pulse that's coming up. You can see it's relatively wide and the color is gray, but it's not a very dark gray. When we come up and hit this boundary, so this is an upward traveling pulse of negative acceleration. When it hits this boundary, now we see kind of a tilting of that, which reflects the fact that the soil here has become softer because pore pressures have been developed. The first part of this wave then enters the loose sand here, where the loose sand has a high pore water pressure and a low stiffness. But that soil will start to dilate as the first part of this pulse applies shear stress to it, so it will become stiffer. So the latter part of this pulse then is entering this loose sand. Well, it's in a stiffer state, and so it will start to catch up with the first part of the pulse. And as we come up through this loose sand towards the surface, we can see that we get a more intensely dark color here, because that upward traveling pulse gets focused in time, much like a shock wave will in a compressible material. And we get a sharper pulse at the surface. And so we can see this is the negative pulse that entered the soil profile. And after a time delay, in order to propagate up through the soil profile, we see that it's much stronger here. It gets reflected back down, then it comes back up. We're going to get here a positive acceleration pulse, the lighter color, and it gets focused in time to a very light color, which corresponds to this pulse. And we see again a negative acceleration pulse being focused in time here and producing a sharp dilatancy pulse. So these strong pulses that occur at the surface are associated with this phase transformation behavior. Here's another one where a relatively broad light-colored pulse enters the softer layer, becomes more focused in time, and it leads to a strong dilation pulse. So we can see these in analyses that capture phase transformation behavior. We'll also see subsequently that we get this kind of evidence out in the field when we have strong motion instruments on top of soil profiles that have liquefied. So let's look at some of the effects now, things that affect the rate of pore pressure generation in soils, in liquefiable soils. Or let's just say in soils that generate pore pressure under drain conditions. So I'm going to go through a series of diagrams here that are going to show simulations that are based on the PM4 sand model that's been calibrated to represent the behaviors of liquefiable soils as we understand them. And then on the right, I'll show some actual data. So here are two sets of two simulations that show the effects of the amplitude of the shear stress. So a 10 kPa shear stress here and 20 kPa down below. Both soils start out with an initial effective stress of 100 kilopascals. And so we often talk about a cyclic stress ratio as the ratio of the shear stress that we've applied to the initial effective stress. So 15 kPa shear stress, 100 kPa initial stress, and that's the cyclic stress ratio of 0.15, here 0.20. We can see that the pore pressures are generated more quickly in the soil that's been subjected to the higher shear stress. It doesn't take as many cycles to come over and reach initial liquefaction with the higher shear stress compared to the lower shear stress. When we look at the results of laboratory tests where we apply different levels of cyclic shear stress and count the number of cycles required to reach initial liquefaction, as the cyclic stress ratio decreases, we can reach liquefaction, but it takes many more cycles. The cycles here are shown on a logarithmic scale. So at a cyclic stress ratio of 0.25, it takes 1 to 2 cycles for liquefaction to be triggered. For a cyclic stress ratio of 0.11, it takes 50 or 60 cycles to trigger liquefaction. So the load amplitude is important. The density of the soil is important. Here's 40% relative density and 50% relative density. You can see that increase in the relative density requires many more cycles to produce initial liquefaction than at the looser state. You can see that the stress strain behaviors differ as well. We get more strain per cycle in the looser soil than we get in the denser soil. And we see this kind of behavior in the laboratory also when we compare these cyclic strength curves with each other as a function of the relative densities of the soil. And And so this behavior is also consistent with the steady state concept. If we have a denser soil, it's going to be less contracted. It's not going to build up as much pore pressure per cycle as the looser soil will. The initial effective stress also affects the state parameter. So two soils at the same relative density but at different effective stresses will behave differently. Now, these are subjected to the same cyclic stress ratio, even though their effective stresses are different. 100 kPa in the upper one, 200 kilopascals in the lower one. They're subjected to the same cyclic stress ratio, so the cyclic shear stresses are greater in the lower one than they are in the upper one, but the cyclic stress ratios are the same. And we can see that the soil at the higher effective stress level is more contracted. And consequently, it builds up pore pressure faster. Not a lot faster, but there's fewer cycles to reach initial liquefaction at the high effective stress compared to the lower effective stress. And we see this in the laboratory as well. So as the effective stress increases for a given relative density or a given void ratio, the cyclic resistance decreases. This is consistent with the state parameter. As we go for a given void ratio, as we move out to the right to higher effective stress levels for a given void ratio, our state parameter is increasing as we're moving across a horizontal line where that steady state line is decreasing. Initial shear stresses produce some complicated effects on the triggering of liquefaction. Here we have two tests, one with a static shear stress of 5 kPa and the other with 8 kPa. And we're superimposing the same cyclic loading on top of that. We can see here that we're having a relatively large reversal of stresses occurring here in the upper test with a lower initial shear stress. Here we barely have a reversal. It turns out that the size of that reversal is significant with respect to pore pressure generation. And so we'll see different effects occurring here. If we have a very loose soil, say 35% relative density, as we increase the static shear stress level, we'll see that our liquefaction resistance decreases. But if we have a medium dense to dense soil, say 55% relative density, as we increase the effective stress, the shear stress, the initial static shear stress that we would see, say, in a steeper slope, the resistance to triggering of liquefaction increases. I messed that up. Steeper slope, we see higher resistance to the triggering of liquefaction. In a loose soil, steeper slope lowers the resistance. So that behavior is complicated. We'll come back and talk about that more later. If we look at the effects of plasticity of the fine-grained soils, or fine-grained component, here's a behavior in a laboratory for some non-plastic soils. Here's a behavior for soils with a plasticity index of 26. We can see differences in the shapes of the stress strain curves. We can see differences in the rate of pore pressure generation. And we see that in this more plastic soil, we start to see a stabilization of the pore pressure generation characteristics at moderately high effective stress levels. So when we're looking at liquefaction, we have to think about when liquefaction is actually triggered. And as I said before, one definition is that of initial liquefaction, which means 100% pore pressure ratio, zero effective stress. And we should recognize that's a temporary condition because the soil will have a tendency to dilate unless it's at a very low density or a very high void ratio. But some soils, like silts and dense sands, will develop a significant amount of strain without ever getting to a condition of zero effective stress. And they behave similarly in this respect. And if that's the case, we often use strain-based criteria to determine the initiation of liquefaction, the triggering of liquefaction. And And sometimes that's expressed in terms of a single amplitude strain, or sometimes a double amplitude strain. So a double amplitude strain would simply be the difference between the peak positive shear strain and the peak negative shear strain. And that's an easy thing to determine if we have a symmetric loading or loading without a static shear stress. If we have a static shear stress or asymmetric loading, we may find that our strains drift off and they become greater in one direction than the other, and that makes the double amplitude strain more useful because we can determine what that value is. If we're highly asymmetric, we may have, say, no positive shear strain and a large negative shear strain. So it's important when we're looking at research on liquefaction papers that describe laboratory studies of liquefaction to understand and recognize what definition of liquefaction is being used. Is it a pore pressure-based definition or is it a strain-based definition? And if it's strain-based, how is it defined? Is it single amplitude or double amplitude, and what level of strain is being used as the criterion? So our cyclic behavior is dominated by the kind of volume change characteristics that Professor Gray just spoke about. They affect volume change under drain loading conditions and pore pressures, stiffnesses, strengths under undrained loading conditions. So we really need to understand and think about the state of the soil, not just its density, but the combination of density and effective stress. It applies to both monotonic loading and cyclic loading characteristics and behavior of the soil. This phase transformation behavior is very important, particularly when we're looking at the liquefiable soils, and particularly when they're under sloping ground conditions, because this stiffening that occurs as they dilate is going to have a very strong effect on permanent deformations. And if we're looking at lateral spreading or some phenomena where we're concerned about lateral movement of the liquefiable soil during an earthquake, the tendency for it to want to move in a down-slope direction is going to be reduced or arrested by this dilation-induced stiffening. That's what's going to keep us from just flowing in one direction over large deformations. So it's important to understand that. It's important to be able to model that. Intermediate soils, like low plasticity silts, tend not to build up very high pore pressures, or at least not extremely high pore pressures, and they're not as strongly dilated. They don't stiffen as much when they dilate as clean sands do. We can see very dramatic changes in the stiffness of the soil at and close to liquefaction in clean sands, and big changes in effective stress and stiffness even within individual loading cycles. The degradation of the fabric of the soil that can occur also affects and reduces the stiffness after liquefaction has been triggered. The rate of pore pressure generation is important. Pore pressures generate faster with high cyclic shear stress amplitudes, with low soil density, with high effective stress, with low plasticity, and can either increase or decrease depending on the density of the soil or situations where we have sloping ground. There are different criteria for the triggering, identifying the triggering of liquefaction. Initial liquefaction is a pore pressure-based definition or effective stress-based definition, but there are also strain-based definitions that can be effective and required and are commonly used when we're dealing with dense sands or with more plastic materials. So now you've seen this morning how important the state of the soil is, both for monotonic loading conditions and for cyclic loading conditions. And we have a good understanding now, as we go through and study these materials, of the basic mechanics of low plasticity soils under monotonic and cyclic loading conditions. And it's important to understand those mechanics in order to be able to evaluate the behavior of these materials. And our procedures, our more practical empirical procedures for evaluating liquefaction potential for triggering of liquefaction, are going to need to be consistent with these principles. And so we'll talk as we move through the day about those practical procedures, and we'll come back to these basic concepts of the behavior of soils and it will help us evaluate how appropriate those empirical procedures are. So I think we'll have a break now, which is about time, and we'll resume at 10:40. 10:20.
Son las 10.
10, sí.